Yes, so I should have mentioned as well when I introduced myself, hi everyone again, that I'm also a CI on the current project. And before I start, I'd also just like to acknowledge the traditional custodians of the unceded lands and waters on which we are meeting today, and also that on which we conducted this research. And I'm joining you today from Wurundjeri country in Victoria, Australia. And so I'd also like to acknowledge my co-authors on this work, which includes members of the team that Ryan was introducing, the Water Quality and Investigations team from the Department of Environment and Science in Queensland, who are one of our industry partners on the linkage, along with Healthy Land and Water from Southeast Queensland.
Sorry, Kath, could you please put in full screen your presentation?
Oh, yes. Thanks, Edgar.
Thank you.
There we go. Okay. So the question, hopefully we've already answered this, and you probably also know the answer to this, but why automate anomaly detection? As we've seen, the volume and the velocity of data are now precluding manual identification of technical anomalies that we're now generating from these high frequency in situ sensors in river networks and in other types of environmental networks. So they're helping to solve that sparsity problem, but by increasing the volume and velocity of the data, we have this essentially a data quality problem that we would like to solve in terms of making sure that the data is trustworthy in terms of its quality and any uncertainty around that quality rating, which we need to address through these automated methods. So the objective for this particular work, which was a precursor to the current ARC, was to develop an anomaly detection framework for high frequency data collected using in situ sensors for end user needs. And so we developed a framework that could be transferable, that offered a step-by-step process at which end users could go through this process together with anomaly detection developers. And so we wanted to make sure that it was very much targeted to end user needs and goals, but at the same time being flexible enough around those needs and goals so that it could be transferable across organisations. And here I should stress that the definition of anomalies that we're using here are that they're the errors in the data caused by technical issues, such as sensor failure, for example. And so we're distinguishing them from what might be real water quality events, which statistically may appear like an outlier or anomaly, but for the purposes of this presentation and for a lot of the work today, we are using the term anomalies to, in association with those errors in the data caused by technical issues. So I'll go through these steps of the framework, step by step, using a case study from data from the Department of Environment and Science, and one of the sites in the network that Ryan took you through. So the rivers that flow out into the Great Barrier Reef in Far North Queensland. And here we're looking at two rivers in particular, freshwater systems, end of system sensors in Pioneer River and Sandy Creek. So the first step of the framework is to identify the industry and end user needs and goals. Now, this is an essential first step because it dictates a lot of the decisions you make throughout the rest of the framework. And for this case study, we were really interested in producing smart graphical outputs for visualization of the data, of the raw data, so that it could be indicated in terms of its known quality in near real time. And I think Ryan made a really good case for why why that was the end user need and goal in this particular case study. The next step is to identify the data characteristics. Now, this is an important step for both the anomaly detection developers and the industry partners or the end user partners, so that together it's really understood what the anomaly detection is for and how the data actually relate to one another in terms of different variables that you're measuring. So for example, in this case, we're looking at turbidity, conductivity, and river level data, how that data behaves through space and time, whether we've got differences between sites or whether there's consistency. And this tells us, for a start, what sort of anomalies we may be tending to get in the data. And that may help decide what sort of anomaly detection algorithm you use. And also the particular patterns of the rivers that we're monitoring. So the next step, so I'm just going to minimize one part of this Zoom so I can see all of my slides. That's what's been, there we go. What's been distracting me. Okay, so the next step of the framework is to define and classify the anomaly types in your data based on their features, patterns, and as I mentioned before, they're patterns in the data rather than the causes of these anomalies. And this goes back to our earlier step, making sure that you're familiar with the data that you're, and the characteristics of that data in which you're wanting to identify the anomalies. So we went through this process together with the department, looking at the data and the types of anomalies that were coming up in terms of the patterns. So we were seeing things like in this time series, hypothetical time series of turbidity data, these things which we named large sudden spikes, for example, labelled here A, where the data observation is extremely different to the previous and the next observation that surround it. We can also have smaller spikes, such as this one labelled J here, or sudden shifts up and down, which are also similar to the spikes, but they only one side of that neighbouring data is offset. So here, for example, we're going along in the grey, and then all of a sudden it shifts upward where it's labelled D to some offset data, which is a different type of anomaly, anomaly type C, and then it's offset back down through a sudden shift to D to the normal behaving data again. We have periods of low, unusually low and persistent data values labelled anomaly type B. We have also periods of unusual high variability data labelled E. We have also things that are impossible values, such as negative turbidity readings or readings that are out of sensor range, so labelled here F and G. And then we have drift, which Ryan gave you a really good example of earlier. We've labelled that H. And then we have gaps of missing data. We label these K. And then our 12th type is any other type of anomaly that we know is caused by an error, but it doesn't fit into any of these other types. And this is an example here, L, where we just have a data point in the midst of all this missing data. There's no way we can, that's basically an untrustworthy data point. And so once we have labelled those, that we've defined those anomaly types, we can then rank them in terms of their importance for being detected based on that end user need and goal that we've defined earlier. And in this case, looking for visual representation of the raw data, things like that sudden spike is extremely important to make sure that that is labelled as a potential anomaly when it goes out to the public. So that's hence why these are ordered A through to K. They're ordered in terms of their importance to detect an anomaly algorithm based on that end user need. And we can see here, if we look again quickly just at the Pioneer and Sandy Creek data, that we've got a few different examples of these in the data sets in the time series for the different variables we're monitoring. And you can also see all these vertical lines are where there's some sort of sensor maintenance or calibration going on. And so that information is also important to gather. I'm not sure what's going on here with my slides, but they're flipping back and forth. I'm not touching anything. Okay, so the next step in the anomaly detection framework is to select your anomaly detection methods. So thinking about everything so far, things that you may want to consider which will affect the decision on what sort of anomaly detection method you choose to use are the importance ranking of those anomalies, what sort of data you've got. Can the different methods handle really big data? Can it handle non-stationary data, which typically water quality data time series is non-stationary? Do you want to be able to run an unsupervised method, for example, so one that doesn't need any training? You don't need data that you train the method on first in order for it to work. Or is a supervised or semi-supervised method okay? So these are all sorts of different questions to ask, which our framework can help you decide on. And for this case study, we're looking at, we've tested 3 different methods. So we looked at rule-based methods, regression-based methods, and feature-based methods. Rule-based methods, anyone can implement these. They're very simple for things that can be hard-coded as to whether it's an anomaly or not without any probabilistic background. So something like identifying gaps in the data or impossible values, you can just hard code for them. In terms of the regression-based method, we trialled a few to see how they'd work. Regression-based methods were using forecasts to forecast an observation based on either the previous data, the naive prediction, the previous observation, sorry, for naive, or a set of previous data to forecast the next one. So they were the other methods, linear regression, ARIMA and Reg-ARIMA, that we used. And then we are able to tell whether it's an anomaly or not based on a specified prediction interval that is developed using a training data set. Now, the feature-based methods, Delaney will talk more about these, and I won't go into a lot of detail other than to say they start with a process of doing a transformations on the data to see the data in high dimensional space to work out which is the best transformation to see particular outliers in the data. And then they use a probabilistic framework in order to assign a probability as to whether the observation is an anomaly or not. Okay, now the next step is to select suitable evaluation metrics. How do you go about knowing whether your anomaly detection method is working or not? So this is in the step where you're setting up the algorithm. So you do need a labeled data set in order to evaluate how the method is working when you're starting off. And a lot of times we use this thing called a confusion matrix. So if you haven't come across this before, I'll just talk you through it. We have in the data, in the time series data, we have anomalous observations and we have normal data. Now, if our anomaly detection method detects an anomaly as an anomaly, it's a true positive, TP. If it detects it as normal data, then this is called a false negative. If we have normal data and our anomaly detection algorithm detects it as normal, it's a false, as normal, it's a true negative. But if it detects it as an anomaly, it's a false positive. And one possible benefit of the last couple of years with COVID is that we may be all a bit more familiar with this terminology now. So for our particular case study, we calculated a range of assessment metrics that are all based around this confusion matrix. So they're quite common. Now, if you're using something like regression, you can also use something like the group mean squared error, and that's also commonly used for regression methods. So here's just a few of some of the possible evaluation metrics, and these are the ones that we used in our case. If you want more information on these, please ask us for the full paper. The next steps are to prepare the data for input into the anomaly detection method. So for example, this may require you to do some transformations, implement the anomaly detection, and then evaluate and compare. Now, the rule-based methods are 100% successful. For the regression and the feature-based methods, I'll take you through some of the key findings and take-home messages that we have from the regression-based methods with the case study. For the feature-based methods, again, please ask us, we can send you the paper, and I've also got links in the presentation to them. Okay, so here we've got the data from the Pioneer River. As you may recall, we've got the time series for the turbidity data from this site in the top row, and then from the conductivity data in the bottom row. Now, the difference between the two panels, the left and the right, in the left panel, I'm showing you the results from the ARIMA. These were the best results out of all the regression-based methods that we used. The results in the left panel are just from straight ARIMA itself. The results from in the right panel are ARIMA with what's called mitigation. This is where there's an extra step that can be implemented after with the ARIMA or with any of these regression methods, whereby if the detection method picks up an observation and classifies it as an anomaly, it will not use that previous anomalous data point for forecasting the next one. It will use the most recent previous non-anomalous data point for forecasting. So that's the difference between these two methods. Now, looking at true positives, true negatives, false negatives, and false positives, what we can see here is some key patterns and take-home messages. With ARIMA alone, we're finding really good detection of sudden spikes, whether these be small sudden spikes, negative sudden spikes, or some large ones, although not all of the large ones, unfortunately, in this particular case study. We're also seeing, if you look at ARIMA and mitigation and turbidity, that we're able to detect some of these more unusual anomaly types. In the light blue, true positives detected here. In the middle of the turbidity time series, it's detected when we implement mitigation, but you can see, looking back to ARIMA alone, the method did not detect that period of unusually high variability. So we're finding ARIMA alone wasn't able to detect some of those more nuanced anomalies, including drift, which wasn't detected here by either method. And we also found with ARIMA and mitigation that although we were able to detect some nice anomalies that ARIMA alone couldn't, we were getting a much higher false positive rate. So the next step in the framework, of course, is to make recommendations. So thinking back on our case study, we found that ARIMA was really useful for an automated anomaly detection, because it encompasses actually a broad range of possible regression-based models. So you may find an ARIMA which integrates autoregressive features, moving average features, and differencing, so a type of transformation, if you will, of the data. It can produce a naive prediction, a straight linear regression, or a full-blown ARIMA of different sorts. So it's actually quite flexible as a method. We also found that ARIMA alone was really quite useful to detect those really important high-ranking anomaly types like the sudden spikes and the shifts. But when we were trying to detect things like drift, we had a high rate of false negatives. However, mitigation might be able to use instead of or separately to detect some of the more complex anomaly types like periods of high or low variability, which might be useful to do things like triggering sensor maintenance, for example. So the really big take-home message of this was that a combination of methods was likely to provide the optimal performance in terms of classification of anomalies while minimising false detection rates. And that we're finding is the case when we're moving on into the ARC linkage project itself, that is carrying on as a key message. So it's something to keep in mind. Not one anomaly detection method may not be all that is needed. We may need to use a few different methods and a combination of them. And finally, communication between end users and anomaly detection developers is absolutely essential. This could not be done with the anomaly detection developers working on their own in isolation or away from the end user. So they were our two really important take-home messages from this anomaly detection framework. And just lastly, before I leave you, I want to mention that there's a range of products and tools that are available from this precursor project, the Anomaly Detection Framework paper. We've got annotated R code and data sets that are available. We have an R package for the use of the feature-based methods called Oddwater. We've got an R-Shiny application, which is really useful to visualize your data, and particularly when you're going through that step of the process when you want to get familiar with the data and its characteristics. And there's links there in the papers listed that were an outcome of that precursor project, where you can find much more detailed information. So with that, thank you.